To process 1080p video at 60 frames per second, a system must ingest and categorize over 124 million pixels every single second. In a traditional software environment, a CPU handles this by grabbing an incoming pixel, looping through a set of predefined color clusters, and executing a distance calculation for each one to find the closest mathematical match. But calculating Euclidean distance requires multiple subtractions, multiplications, and a square root. Executing this heavy arithmetic inside a continuous loop consumes too many clock cycles. The processor inevitably falls behind the incoming video feed, and the system begins dropping frames. This diagram illustrates the bottleneck. On the left, a CPU processes massive distance metrics sequentially, its logic looping and choking data flow. On the right, the solution, a massive parallel hardware pipeline spreading operations physically across the chip. To maintain full wire speed, algorithms must bypass software loops entirely and be mapped directly onto raw silicon. Designing for hardware means adopting an entirely different set of rules. The baseline requirement for this architecture is rigid. The system must process exactly 1 pixel every single clock cycle. There is no buffer to save the system if a calculation takes too long. 0 stalls are permitted under any condition. This creates a mandate for deterministic latency. Unlike a CPU, where execution time fluctuates based on system load or interrupts, an FPGA timeline is perfectly uniform. The time between a pixel entering the chip and the clustered result exiting must be a fixed, unvarying constant. To achieve this predictability, the architecture uses spatial parallelism. We stop asking a processor to repeat a task over time, and instead build multiple dedicated circuits to do all the tasks simultaneously. Ultimately, we are trading time for space. We dedicate more physical silicon to build a rigid, multi-lane highway for the data, ensuring the calculation time remains absolute. This schematic represents the blueprint for mapping k-means to silicon. The horizontal axis represents time, mapping the computational pipeline. The vertical axis represents space, the 30 simultaneous hardware instances. At this intersection, pixel data drops from the pipeline and broadcasts into those dedicated cluster units simultaneously. But before the system can cluster anything, it has to safely ingest the raw video stream. Driven by a strict system clock, the incoming 24-bit RGB stream is captured and sliced into separate 8-bit red, green, and blue components. Alongside color data, the chip captures critical video control signals, the valid flag, start of frame, and end of frame. Because the mathematical pipeline ahead will take exactly 25 clock cycles to complete, these control signals must be artificially delayed by that exact same amount through a series of internal registers. Locking every incoming bit to the system clock guarantees that the newly clustered pixel perfectly aligns with its original position in the video frame. Hard-coding target color clusters into the silicon would make the system too rigid for dynamic video. The architecture requires a mechanism to manage the k-means centroids on the fly. Based on configuration inputs, a multiplexer selects a specific color palette from a bank of deep lookup tables. Up to 30 unique centroid targets are loaded into parallel hardware registers simultaneously, fully loading the hardware. This setup enables spatial unrolling, the physical act of abandoning the software loop entirely. A single incoming pixel on the left is broadcast outward, its data split into 30 independent paths. The data arrives at 30 separate cluster cores simultaneously. Each core already holds a unique centroid target from the orchestrator and executes the comparison instantly. By laying the algorithm out physically across the chip, the hardware executes 30 separate distance calculations in a single clock cycle, eliminating the iteration bottleneck. Inside each of those 30 dedicated clustering cores, the real hardware arithmetic begins. In the first cycle, the logic calculates the absolute difference between the incoming pixel's color channels and its assigned target. For the Euclidean distance, the differences for red, green, and blue are individually squared and fed into a summation node. Summing these 16-bit squared values without overflow requires the internal precision to instantly jump to a 32-bit register, shown in the accumulation block. Now the system holds a 32-bit sum. To finish the Euclidean distance metric, it must find the square root of that number. This schematic highlights a fatal hardware limitation. Attempting to calculate the square root of a 32-bit integer in a single clock cycle requires a logic chain but is too deep for high-speed silicon. The electrical signals simply cannot propagate through all the necessary logic gates before the next clock pulse arrives, resulting in a timing violation that crashes the system. The pure architectural rescue for this physical logic wall is deep computational pipelining. The complex square root operation is shattered into 16 manageable hardware stages. On every clock cycle, each stage consumes 2 bits of the 32-bit number, updates a partial remainder, calculates the next bit, and passes the result down the chain. Complex, heavy arithmetic does not break real-time systems as long as you shatter the math across the temporal axis. You sacrifice initial latency, waiting 16 cycles for the first answer, but in return, you secure sustained, unstoppable throughput. As the data exits that pipeline, the system holds 30 simultaneous Euclidean distance scores, one for every possible color cluster. The challenge is to instantly find the global minimum out of those 30 variables. The solution is a synchronized reduction tournament. All 30 variables enter a bank of comparators in the first clock cycle. The lowest values advance to the semifinals in cycle 2 and to a single decisive comparison in cycle 3, yielding the global minimum. Because this decision-making logic is strictly pipelined, it guarantees the winning color cluster is selected without ever stalling the forward flow of the pixel data. The computation is complete. The system replaces the original raw pixel with the winning color cluster, and the data is ready for output. This timing analysis visualizes the architecture's mathematical certainty. Trace the timeline from the input pixel at T0 directly to the output pixel at T25. This code explicitly locks the output exactly 25 cycles behind the input, ensuring perfectly predictable video synchronization downstream. But building a system this rigid comes with significant engineering trade-offs. This chart contrasts physical costs against performance benefits. Instantiating 30 parallel arithmetic units consumes massive logic gates and causes heavy routing congestion. The physical footprint is large. In return, you get 0 stalls and a guaranteed processing rate of 1 pixel per clock cycle. The final architecture illustrates the absolute rules of hardware acceleration. Parallelism beats iteration, and strict synchronicity ensures reliability. True real-time processing isn't achieved by simply running a processor faster. It is achieved by building rigid, application-specific silicon highways that trade flexibility for unstoppable throughput.